Okay, so the first announcement is that the TA office hours will be moved from to Thursdays, 10 to noon. And the place will be to be announced. So I'll probably just send out an email. Maybe you guys tomorrow can figure out the room and then let me know, and I'll send out an email. By the way, did everyone get the email announcement that I sent out last week and earlier this? Okay. If you didn't get email announcements, that means I don't have your email address, so send me your email address. Another announcement I did, there were a couple of tiny little typos on the problem set. A few more that I still haven't corrected. They're all kind of, I think, the sort of thing you might not even notice, but some people notice them. Okay, so I'll send out a corrected problem set. Sorry about that. You know, typos of that sort are sort of hard to avoid, and these will, I'm sure, be the first of many. Okay, good. So let's go ahead and do some physics. So let me remind you of where we left off last class. So last class, we were discussing the quantization of a free scalar field denoted phi. So the action of the free scalar is quadratic in the field phi, and it takes the form of an integral over all of space-time times a kinetic term involving the second derivative of phi along with a potential term that tells us the mass of the scalar field. And the solutions to the equations of motion obey the Klein-Gordon equation, which was a familiar-looking second-order differential equation for phi as a function of space and time. So to quantize, we think of phi not as a classical field, but rather as a quantum mechanical observable, that is to say, a Hermitian operator acting on some Hilbert space. And we take this Hermitian operator and we simply expand it in terms of some Fourier basis. So in particular, we write it as an integral over all possible momentum modes labeled by some three-dimensional momentum p. And we had 1 over the square root of 2 omega p times some operator that we called A. So here, P vector labels the different momentum modes, and omega P was the energy, with an exponential factor. Thank you, e to the ip dot x. So omega P is the energy of a mode with spatial momentum P. So just to remind you a little bit of the context, so we're working in Schrodinger picture here. So we have 1 degree of freedom per point in space, okay? And so we think of phi as a function of x, not of t, because in Schrodinger picture, the operators are independent of time, but the wave functions or the states evolve in time. That means that we think of our field operator phi as a function of x. X here you can think of, x vector here you can think of as a label that labels different degrees of freedom. And we regard phi of x as an operator for each point x in three-dimensional space. And all I've done here is a Fourier transform. So instead of working with operators labeled by x, I'm now going to work with operators labeled by some three-dimensional vector p. And remember last time we saw that if you work in Fourier space in terms of the momentum modes labeled by p, the equations of motion were just that of a bunch of harmonic oscillators. So 1 simple harmonic oscillator per momentum mode p. And what I called omega sub p here was just the frequency of the harmonic oscillator with momentum p. There was a similar expression for the conjugate momentum pi, which is the dual variable to phi, in the same sense that x and p are dual in traditional quantum mechanics. So this can also be Fourier expanded. and there was a sort of conventional normalization factor. So all of these omega p's and i's and 2 and stuff like that, these are just some normalization factors that we've inserted for a future convenience. And there was a similar expression for pi. Okay. So I should emphasize here that at this point I have done absolutely nothing. All I have done is I have taken my position and conjugate momentum variables, phi and pi, and I've written them in momentum space instead of position space. Okay. That is to say, instead of thinking of a set of observables labeled by a position x, I'm thinking of a set of observables labeled by a position, a point in momentum space, p. Okay. And I'm calling the Fourier modes of the operator phi a and a dagger. And what I'm not doing is assuming that a is a Hermitian operator, which is why I've written a and a dagger separately. Just as when we quantize the harmonic oscillator, we write x and p as linear combinations of a and a dagger, the raising and lowering operators for the simple harmonic oscillator. So if I wanted to, I could rearrange these equations to write explicit expressions for a sub p and a sub p dagger in terms of phi and pi. Actually, that's a nice exercise. It's not one I assigned to you, but it's something that if you're a little unfamiliar with this, you could go through and do on your own, at some point if you're bored. So just as a check, you can stare at these equations and hopefully convince yourselves that phi and pi are Hermitian operators. Take the Hermitian conjugate of phi. That will interchange these two operators here. And similarly, take the Hermitian conjugate of pi. It'll interchange those two factors there, and you'll get another minus sign because of the complex conjugation of the I there. And the important point that we verified yesterday, or last class, is that the canonical commutation relations the analog of the statement that the commutator of x with p in quantum mechanics is equal to I times h bar take a very simple form when written in terms of the operators a and a dagger. In particular, they just become the statement that the a's and the a daggers obey essentially the simple harmonic oscillator commutation relations. So here, what we have, if you look at this equation that I've written down here, are an infinite set of simple harmonic oscillator commutation relations. So there's some 2 pi cubed there. That's just some convention to make some of the equations look simpler. But the important point here is that AP and A dagger P prime commute when P is not equal to P prime. So, but when P is equal to P prime, they don't commute. Now, if we were considering a finite number of harmonic oscillators, we would choose some normalization where their commutator would be equal to 1. But here we have a continuum of harmonic oscillators. And so the thing to do is to choose them to be delta function normalized so that their canonical commutators take the form of this 3-dimensional delta function. In the problem set that you turned in last Friday, you worked out the Debye model, which was essentially a 1-dimensional version of this, where you had the different frequency modes for the Debye model. There were a finite number of them, and all of the different frequency modes, there were raising and lowering operators associated with them, and they obeyed the standard simple harmonic oscillator commutation relations. And if you wanted to, you could have gone ahead and taken the n going to infinity limit of the expressions that you derived on that problem set, and you would have derived precisely this set of commutation relations here. So this is really, this class is an extremely important lecture today because this is really kind of at the heart of quantum field theory, really. That when you consider a free quantum field theory, Everything just boils down to a set of harmonic oscillators. So what I'm going to do for you today is continue what we discussed last time and work out the Hamiltonian of the theory in terms of these harmonic oscillators. And no surprise, it's going to be an infinite number of copies of the simple harmonic oscillator Hamiltonian. But before I do so, let me just pause and see if there are any questions. Is everything more or less clear? Good. Okay, so let's go ahead, as promised, and work out the Hamiltonian of the theory. And this is the sort of computation that you should hopefully become familiar with, in particular for the problems that this week you're going to need to do this in a slightly different example. So remember, what was the Hamiltonian? This is something that we worked out last class. So it's an integral over all space of a kinetic term, which is 1/2 momentum squared, a potential term coming from the gradient energy of the scalar field, plus a potential term coming from the m squared phi squared term in the Lagrangian. So this is the Hamiltonian. And in order to compute this in terms of the raising and lowering operators A and A dagger, all we need to do is insert these expressions here into our expression for the Hamiltonian. Okay. And so that's what I'm going to go ahead and do. So in particular, so H is now, so first of all, we had an integral d3x, and then we have to integrate over a p and a p prime, which are the expansions. So let's imagine that we're computing that pi squared term first. So we have a pi squared. So it's an integral d3p, integral d3p prime, with some denominator, which is 2 pi to the 6th. There's a coefficient out front, which is 1/4, because there's a 1/2 here, and then a 1/2 when you square those two, 1 over square root of 2's. And for that pi term, what do you get? Well, there's a minus sign, which comes from squaring that minus I. And then there's a square root of omega p times omega p prime. I should really be putting vector indices on those p's to remind ourselves that it's a 3 vector, but sometimes I'll be a little sloppy and probably forget about those. And then we just need to insert these harmonic oscillators here. So we have, here actually let me rewrite this to put the factor, the exponential factors first. So we had an e to the I x dot p plus p prime. And then we had, what was it, the square root of omega p prime times ap minus a minus p dagger times ap prime minus a minus p prime dagger. Okay. So I think I've got all the factors there for the pi squared. Any questions on that? I haven't done anything too fancy yet. Oh, and I forgot to include the minus sign out front. Good, that one will be important. Any other questions? Yes?
Quick question. When you consider pi squared, don't you consider the conjugate of pi, or is that not relevant?
By conjugate, what do you mean?
The complex conjugate of pi, because
Oh,
there's an I.
in the problem set, pi is a Hermitian operator, so you should think of it as a real number, essentially. So it doesn't have a complex conjugate. On the problem set that you're doing, you'll consider the case where pi is a complex number, and it will have a complex conjugate, or Hermitian conjugate that you would call pi star. But remember, this is an operator equation, and that factor of I here is precisely to ensure that pi is Hermitian, right? Because when you take the Hermitian conjugate, these two factors here got interchanged. So you should think of pi as a real number, right? Because this expression here is the difference between A and its Hermitian conjugate. The difference between a number and its complex conjugate is purely imaginary. Good question. Any other questions? Okay, so since it's not so let's go ahead and then write down the other terms. So let's first think about the grad phi squared term. So the expression for phi, unfortunately I can't quite fit them all in the same transparency. The expression for phi, so when you take the gradient here in the Hamiltonian of phi, that gradient just hits this exponential factor here, and it brings down a factor of IP. So that means that if you want to write the terms involving phi squared, what do you get? Well, we have this normalization factor, so there's a 1 over the square root of WP prime, okay, in the denominator. And what's the numerator? Well, you got a factor of IP for each of those gradients. And so you get a minus P dot P prime here. And then this term here will just give you a plus M squared. And then we had to square this quantity here. So that was AP plus AP dagger times AP prime plus AP prime dagger. Good. Any questions so far? Yes. Another minus. A dagger minus P. Oh, they're minuses. Yes. Thank you. Good. Good. Other questions? I'm going through this computation in a fair amount of detail because it's a very important one. You're going to have to get used to doing computations like this on your own because this is not the first time that I will expand a field in terms of harmonic oscillators. We're going to do it again and again every time we have a new field theory we want to consider. Going through it in some detail right now, but in the future I'll be doing it much more quickly, or you'll be doing it. Good. So the first thing that we want to do is we want to do the x integral. So the x integral gives you a delta function. So the integral d3x of e to the I p e to the I x dotted in to p plus p prime gives you 2 pi cubed times a delta function that sets p equal to minus p prime. So we can then go ahead and use that delta function to do the p prime integral. And you're left with an integral d3p. And if you set p prime equals to minus p, well, first of all, a lot of miraculous things happen. So omega p prime is equal to omega p. So we can just pull out all of those omega p's. The second thing that happens, or I did that a little quickly. So the first thing that we notice is that if p prime is equal to omega p, then this term here, that just becomes omega p. Or let me say that a little bit more clearly. So this term here then becomes omega p squared over omega p, which is omega p, because the numerator is just p squared plus m squared, otherwise known as omega p squared. So you have an overall power of omega p that you can pull out. And then it's just a matter of simplifying those expressions involving the a's and the a daggers. So if I did everything carefully here, you can look at the terms, say here, where you have an AP times AP with an overall minus sign up front coming from here, and then that'll cancel an AP squared term coming from those two. So the only terms that don't cancel are the ones that involve one A and one A dagger. And what do you get? You get an AP dagger AP, say, coming from this term times that term, okay, plus AP dagger, all over 2. Good. So This is something you may or may not recognize. We can put it in a somewhat slightly more familiar form if we use the fact that the commutator of AP with AP dagger is a delta function. So you can write this as the integral d3p over 2 pi cubed omega p times AP dagger AP plus, well, let's call it 1/2 times the commutator of AP with AP dagger. Now, if you remember our harmonic oscillator algebra, you remember that the commutator of AP with AP dagger is a constant. But we've normalized so this is just some constant here. And remember, we're computing a Hamiltonian, and an overall constant added to the Hamiltonian just reflects some shift in the ground state energy of your system. So what one can do is just throw this away and declare that we're going to choose the ground state energy of our system so that the ground state has energy 0, or energy 12, or energy whatever you like it to have. So if we set this equal to 0, what we get is an integral d3p over 2 pi cubed times omega p times AP dagger AP. Now, hopefully you're all sort of upset at this point, because one of the things that I just made a big deal about is the fact that our oscillators are plane wave normalized, so that their commutator was a delta function. So if I were to try and do this super precisely, I would have a delta function of 0, which is infinite. So what you've discovered here, or what we've discovered here, is that, formally speaking, when you quantize a scalar field, you find some sort of ground state energy that is infinite. But of course, this infinity is unobservable. And unobservable infinities are something you're just going to have to get used to in this class. So in particular, this is but the first of many divergences that we'll encounter in this class. It's by far the simplest, and one that we can very easily convince ourselves should be ignored, because it's a divergent contribution to the ground state energy of the system, which is something that's intrinsically unobservable. Okay? If I handed you a harmonic oscillator where the ground state energy was, a keV, and then I handed you a different ground state energy harmonic oscillator where the ground state energy was 1,000,000 times that, there's no experiment that you could do on one of those harmonic oscillators to determine the overall value of this ground state energy. All you can do is do things like measure differences in energy levels of the system. The value of the ground state energy is unobservable, and so for that reason, we really don't have to worry about it at this point. I will make one point here, which is that even the infinite ground state energy, there are circumstances under which it's going to be useful to talk about this infinite ground state energy. So in the problem set that I'll be handing out on Thursday, you'll explore the behavior of this divergent contribution to the ground state energy in a little bit more detail. And in fact, later on in this class, I'll hopefully give you a problem where you study it in a lot of detail and use it to compute what's called the Casimir force. So it's a force between parallel plate capacitors that arises because of this sort of essentially apparently infinite contribution to the ground state energy. But for now, I just want you to content yourselves by telling yourself whatever it is you need to do to get to sleep at night, namely that this is an infinity, but it's unobservable, and so we're not going to care about it for now. Good. Okay, but just with that sort of subtlety aside, what do we see here? What we see is that the Hamiltonian is exactly the Hamiltonian of an infinite set of harmonic oscillators. One per momentum mode p. And this coefficient omega is just the prefactor, which tells you the energy of the harmonic oscillator. So this is the frequency of the mode p. Just so that you remember, and hopefully this is something that you reminded yourselves of on the first problem set, this operator AP dagger AP is also known as the number operator. And so it measures, so let me just remind you, for those of you who might not remember, the Hilbert space of a simple harmonic oscillator is infinite dimensional. And the basis states for the simple harmonic oscillator are built by starting with a vacuum state, which is defined by the property that it's annihilated by a lowering operator. And then you have a bunch of other states. So you have the first excited state of the system, where you take a dagger acting on the vacuum state, the second excited state of the system, where you have two A daggers on the vacuum state, and so on and so forth. So this is the Hilbert space of a single simple harmonic oscillator. The number operator, A dagger A, just measures the number, which state you're in. So the number operator acting on the state 2, for example, just gives you 2, and so on and so forth. Here, maybe I'll write this as 0 times the vacuum state. So that's a single harmonic oscillator.
1.
Yeah, okay, 1. Yes, fine. Thank you. Good. Excellent. Paying attention. So this is a single harmonic oscillator. So for free quantum field theory, the Hilbert space is just that of an infinite number of harmonic oscillators. One per momentum mode p. So what do the states look like? So there's going to be a vacuum state, which is defined by the property that it's annihilated by all of the lowering operators for every momentum p. The other states are found by acting with this vacuum state with the raising operators. So for example, AP dagger acting on the vacuum state will be a state which has a particle of momentum p. Similarly, the state acted on by 2 of these raising operators will be a state with 2 particles whose momenta are p1 and p2, and so on and so forth. In this Hilbert space, you will have states where you can have any number of particles with an arbitrary configuration of momenta. So this is sort of easiest to think about, again, if you think of our mechanical model of a scalar field theory as a bunch of masses connected by strings. The classical solutions were propagating waves with some frequencies that depended on the momenta of the wave. And when you quantize, those propagating waves are associated with quantum states, which in the case of our mechanical model of balls and springs would be called phonons. Okay? They would be the quantum states of the traveling waves of this collection of masses and springs. And more generally, in other sorts of quantum field theories, we would call them particles. Question?
Regarding that ground state energy, the thing that you're saying that one cannot measure the ground state energy of a harmonic oscillator, are you saying that one observer inside the system cannot observe it?
That's a very important point. What I'm saying is that if I have, the harmonic oscillator and I have some other system that is coupled to it, then one could observe the difference between the ground state energy of that harmonic oscillator and the system to which it is coupled. Okay? But if you just looked at the harmonic oscillator itself, then it would be unobservable. So that's an important point. For example, when we write down the Hamiltonian of the universe, okay, you can shift the Hamiltonian of the universe, you can shift the ground state energy of the Hamiltonian of the universe by an overall constant, right? And that constant is unobservable. But once you start dividing the universe up into bits and pieces, you don't get to freely shift the ground state energies individually. Okay? Yeah. So when you try and study this divergence a little more formally, as you will do on your problem set, you should really think about the ground state energy of the quantum field theory that describes our universe as being shifted once, okay? Because you get one, you get one divergence for free. Okay? And in fact, later on in this course, when we study renormalization, we'll understand a systematic theory of those divergences, which ones can be removed, which ones can't, what does it mean for the formalism of the theory, how do we account for that, and so forth. Good question. Yes. Other questions? Good. Okay. So a couple comments are in order. So the first thing that you should do is that you can check, so by definition, the Hamiltonian operator acting on the vacuum is equal to 0. Remember, the Hamiltonian operator was the integral d3p of omega times a dagger A. A annihilates the vacuum, so H acting on the vacuum is equal to 0. Similarly, you could compute, say, H acting on a one-particle state. And remember, H is just the sum over all P of omega P times the number operator which measures the number of excitations of momentum P. And so this will just be omega P times AP dagger acting on the vacuum. Okay. What is that? That's just the statement that a particle with momentum P has energy omega P. Similarly, one could go ahead and compute, say, the Hamiltonian of AP1 dagger, AP2 dagger acting on the vacuum, and that would be omega P1 plus omega P2 times AP1 dagger, AP2 dagger acting on the vacuum. What is that? That's the statement that if you have a two-particle state where you have a particle of momentum P1 and one of P2, then their energies add. I should mention the fact that their energies add in some simple way is really a consequence of the fact that we have a free scalar field theory. So these harmonic oscillators aren't interacting with one another. When we consider more interesting quantum field theories, namely interacting quantum field theories, the story is going to get more complicated. So one other comment I'll make is that because these A daggers commute with one another, the particles that we're constructing here have Bose-Einstein statistics. So in your class on quantum mechanics, you probably encountered spinors, which have opposite statistics. But the particles that we're constructing here have simple Bose statistics. Okay? They don't obey an exclusion principle. So remember, particles that obey an exclusion principle are ones, well, we'll consider them in much greater detail in this course. I mean, a large part of this course will be devoted to them. But particles that obey an exclusion principle have the property, for example, that you can never construct a state of the system where two fermions are in the exact same quantum state. Whereas here you can see that you can construct an operator, you could construct, for example, this state, which is a two-particle state. And two-particle states only exist for bosons rather than fermions. So later on in this class, so in fact, maybe if I can think of a good exercise, I will. In fact, what one could try and do is one could try and quantize a scalar field in a way that would make them fermions instead of bosons. In order to do that, you would have to replace that commutator here, all of the commutators in the harmonic oscillator algebra, by anti-commutators. And if you do that, you can actually show that the theory is sick, that the energies are unbounded below, that there's no nice ground state, that you break all sorts of symmetries and stuff like that. And in fact, it turns out that's not an accident. So it turns out that in quantum field theory, at least in 4 space-time dimensions, the spin of a particle is related to its statistics. So the fact that we're studying, and that's a sentence that we'll be unpacking more later on in this class. But in the present case, what that means is that because we're considering particles that are scalars, namely those which assign a number to any point in space, as opposed to spinors, say, which are described by a collection of numbers at each point in space, it turns out that the only way to quantize this system is by treating these particles as bosons. So later on, in the next couple of weeks, probably, we'll encounter particles that need to be treated as fermions rather than bosons. So you guys, just for my information, how many of you, you see fermions and bosons in your quantum mechanics classes, correct? And you understand, you probably didn't see the fermionic oscillator, is that correct? Okay, that's good for me to know. I'll give you a problem set on that. Good. One more comment that I'll make. So we started out our discussion last class with Noether's theorem, and using Noether's theorem to compute the Hamiltonian, which was the conserved quantity associated with time translation. But I could have just as well computed the momentum, which would be the conserved quantity associated with spatial translation rather than time translation. Again, this is a great exercise that I would encourage you to work out. So P, which is the conserved momentum, so in terms of the stress tensor that we wrote down last class, this would be some integral d3x of some component t0i of the stress tensor. So what is this? This is going to be the integral d3x pi grad phi. Okay. So I'm not going to prove that to you. Let's call that an exercise. So if you don't believe me, you can go ahead and compute it for yourselves. It's quite straightforward. I wrote down the stress tensor for you last time. You just need to figure out which components of the stress tensor to integrate and then plug in the Lagrangian of the free scalar field. And this expression will pop out. And then if you go ahead and plug in our expression for the pi's and phi's in terms of those raising and lowering operators, you get an expression that looks like this with some prefactor that sits there. Can anyone guess for me what that prefactor is? So let's just stare at this equation and then maybe you'll be able to guess it for me. So what is this? This is the integral. So this is the conserved momentum, which is supposed to be the total momentum of the system of some collection of particles. And we have the integral d3p, where p is an index that labels the different momenta of the particles, times this number operator, A dagger A, which measures the number of particles of momentum P. And so what should the prefactor be if you want to measure the total momentum of a collection of particles? P. Good. So if you stare at that expression for a second, you should be able to convince yourself that what is this? All this does is that if you take it, for example, and you act on the vacuum state, you'll get 0. Okay, great. That means that if you have no particles, they don't have any momentum. Act on it with a state with one particle of momentum, little p, and you just get little p times AP dagger acting on the vacuum, and so on and so forth. If you acted with this on a particle state where you have an AP1 dagger, AP2 dagger on the vacuum, you get a prefactor of P1 dagger, P1 plus P2. It's important here to distinguish between the thing that I'm calling capital P, which is the total conserved momentum of the system, and little p vector, which is the label that I'm using to label different modes. Hopefully, that's not too confusing. Okay? But, you know, it's hard for me to come up with a name other than P for the momentum. I guess I could call it K, couldn't I? Well, it's too late now. Good. One other final comment, just as a matter of terminology, which is that the Hilbert space of a free scalar quantum field theory is often known as a Fock space, F-O-C-K, and the raising and lowering operators are known as the Fock space raising and lowering operators. And sometimes you might formally see the Hilbert space written as a tensor product of a bunch of simple harmonic oscillator Hilbert spaces. Okay. So that's just some fancy mathematical notation for something you already know, which is that the Hilbert space is the one that I wrote down for you above. But for those of you who've seen tensor product notation in your quantum mechanics classes, this is literally the statement that, you know, if you have two harmonic oscillators that are decoupled, then the Hilbert space describing two harmonic oscillators is the tensor product of one harmonic oscillator Hilbert space with the other harmonic oscillator Hilbert space. And this notation here just says that you do that for all possible values of P. Okay? So you just take a bunch of different tensor products. If you're not familiar with this sort of tensor product notation, then don't worry about it too much. It means exactly what we said earlier. Questions? So what I'd like to do for the rest of the class today is just spend a little bit more time getting to know this Hilbert space, the Hilbert space of a free scalar field theory. If I have time today, what I'd then like to go ahead is reconsider the question of causality in free scalar field theory. And we'll see how it is that the theory of particles that we've constructed so far evades the result that I described to you in the first lecture, where if you have a single particle relativistic Hamiltonian, you could go back in time and cause all sorts of trouble. Okay? But let's first spend a little bit more time getting to know this Hilbert space. So the first thing to state is that we should normalize our states. So I'll normalize my vacuum state so that it has norm 1. Okay. That makes pretty good sense. But what I'll then do is, what I want to do is I'll let P denote a single particle state, so a state with a single particle of momentum P, which I told you should be AP dagger acting on the vacuum state. And I'm going to introduce a prefactor here. So I'll call this 2 EP, okay, where EP is just the energy of the pth particle state, of a state of a particle with momentum P. So It's what we called omega p earlier. I'm introducing the symbol EP because we're going to later on be generalizing this to cases where the formulas will be a little simpler and we might not have just simple harmonic oscillators, but states with more complicated dispersion relations, that is to say more complicated expressions for the energy in terms of the momentum p. Okay? But right now EP is just the expression for omega p that I wrote down above. And so P is going to be the one particle state. And it's normalized in a sort of funny way. It's normalized so that when you take the inner product of a state of momentum P with a state with one particle of momentum Q, you get a delta function, so that sets P equals to Q, but with a prefactor that is linear in the energy of the state. Okay. So, you might thought that the most sensible thing to do would be to normalize our states without that funny factor of the square root of 2 EP out front, so that you would just get a delta function in the normalization factor. But the point is that this three-dimensional delta function is not Lorentz invariant. It treats space and time on unequal footings. So if you worked in a different frame, you would have to take into account the fact that our states, the normalization of our states would change. In fact, this normalization factor, EP, times this three-dimensional delta function is Lorentz invariant. What does that mean? That means that if you were working in a different frame of reference, one that was moving with some relative velocity v with respect to your original frame of reference, then you wouldn't have to change. This factor would be unchanged. You would still have E times the delta function in that new reference frame. And you will show this on the problem set. And in a related point, actually, no, I'll save that for later. Okay. So, for example, the P's are a basis for one particle states, so that, for example, if you want to use the relationship in quantum mechanics that the identity operator is the sum over all states in the system of the projection operator on those states. So have you guys seen that before? This is the fundamental statement that a set of states form a complete basis for your Hilbert space. So if a set of states n, so n is a label for a set of states that in a basis of a Hilbert space, if they're normalized appropriately, then that's essentially the definition of this statement here. So with this normalization factor for P that I've introduced, you can think about the basis states for a free field theory in terms of, say, the state with no particles plus the states with one particle labeled by a momentum P, plus analogous expressions for a state with two particles. And then the point of our normalization factor is that you'll have a factor of 2 EP here in the denominator. Okay. So this denominator here comes from this expression here for the norm of the states. One could check this expression, for example, by acting on it with some single particle state of momentum K, for example. Or Q, I guess. Okay. Any questions on this so far? And then there would be analogous terms for 2 particle states, 3 particle states, and so forth. So we've really finished our quantization of free scalar field theory here. We have a Hilbert space. We have a Hamiltonian acting on that Hilbert space. But before we continue with our discussion of quantum field theory, I think it's worth returning for a second to consider the initial observables in our system. Okay. So the observables in our system were the scalar field operator phi. And I think now that we have an expression for phi in terms of these raising and lowering operators, I think it's worth thinking for a second about exactly what the physical interpretation of phi is. So what is phi? Well, I should imagine taking the operator phi and acting on the vacuum state of the theory, a state with no particles. Then what would you get? Well, you would get the integral d3p over 2 pi cubed. So let's just go up and remind ourselves what phi was. So this was our expression for phi here. You act that guy on the vacuum, and the AP will annihilate the vacuum, and you're left with an AP dagger. And then you have an e to the I p dot x times the state with momentum p, along with a normalization factor that was 2 EP. So what does that mean? That means if you take a state with nothing there, and you take the field operator phi at a point x, and you hit it, and you act it on the vacuum, you get a bunch of particle states, one for every momentum p. And in fact, I think this expression looks a little bit clearer if you take the inner product with some particle of momentum q. Then that that inner product of q with p gives you a delta function that sets q equals to p. And the normalization factor, so remember we had this 2 EP normalization factor. So this just gives you an e to the I q dot x. Okay. So what is that? That's the wave function for a particle of momentum q. Or, to say it another way, it's the wave function of a position eigenstate in momentum basis. So this is the wave function for a position eigenstate at a location x in the momentum space. So what is the field operator phi? Well, phi, that means that phi is the operator that creates a particle at a position x. You took phi and you acted it on the vacuum, and then you got a single particle state. Now, there's one slight subtlety here, which is that I took phi and acted it on the vacuum. You could ask what would happen if I took phi and acted on a state where there were already particles there. Well, remember, phi had A's as well as A daggers. Okay. So that means that phi doesn't just create a particle. It can also remove a particle. So the physical interpretation of your field operator phi is that it's the operator that creates or destroys a particle at position x. The problem being that the Hamiltonian looks sort of complicated in position space and is much simpler in momentum space. So usually we like thinking about the observables and the Hilbert space of quantum field theory in momentum space rather than position space. But there's really no reason why we couldn't also work in position space if we wanted to. So what I wanted to do, so this really completes the quantization of the free scalar field. I mean, there's a few things that I wanted to say about causality and Green's functions and stuff like that, but this is really, you know, the basics. So let me pause and see if there are any questions. Yes?
Yeah, I have a good question. Because there should be like infinite number of degrees of freedom in this field, and on the right side we have an integral, and I'm just dumb to see where the degrees of freedom.
Where are they? Well, if you look at this, no, that's a good question. So here you have phi, there's an infinite number of possible field variables, phi, labeled by different points. And here what you have is you're rewriting it in terms of the infinite number of possible momentum modes. Okay. And so, you know, you have these different states. You take phi at x acting on the vacuum, and all of them can be written as a linear superposition of these momentum modes, because, you know, the momentum modes form a basis for the one particle states. But the difference is what their phase factors are. I mean, I'm not sure if I'm completely answering your question, so maybe let me say one more thing, is that when you work with phi of x, that's an infinite number of degrees of freedom, one per point in space-time. All we've done in this lecture is replace that with a different way of writing those infinite number of degrees of freedom. Instead of writing 1 degree of freedom per point in space, we write 1 degree of freedom per momentum mode. All we did is we diagonalized the Hamiltonian, right? Yeah.
We have a superposition, I understand that, but like which one of those functions or like regarded as functions, like which one has the degree of freedom? Like,
Well, remember,
free to choose our
good.
phase, or
So I'm writing down a state here, not an operator. So it is still labeled by x, okay? So maybe I should say it a different way. What I'm doing is I'm writing down the matrix element. So phi is an operator. And what I'm doing is writing down the matrix elements of the operator phi in momentum space. That's another way of saying what I'm doing. Well, I didn't write down the full formula because then I would have to, well, I'd have to write down a few more things, but yes. Yeah, maybe, does that make it a little,
yes,
little clearer? Right. Okay. Yeah, I mean,
yeah, because I just
yeah,
trying to imagine like how,
right.
how different
Let's put it
states would be like.
let me put it this way. If you think of our original mechanical picture of balls on springs and stuff like that, what were the degrees of freedom? You know, in position space, the degree of freedom is you take the vertical location of one of the balls on the springs and you move it up or down. That's the degree of freedom. Now, what I'm doing is I'm trading that for the degrees of freedom where I look at the propagating wave solutions. That's all I'm doing here. And just as we had an infinite number of different balls that we could imagine displacing vertically, we have an infinite number of different normal modes. So like in a mechanical system with a finite number of degrees of freedom, if you work around an equilibrium point, you would work in terms of the normal modes of the system, which diagonalize the Hamiltonian. That's exactly what we're doing here. Yes? Up to constants, pi does exactly the same thing. The difference is the relative, yeah, good point. The difference is the relative phase factor. Remember, we're talking about amplitudes, quantum amplitudes. So signs and factors of I are important. And the only difference really between pi and phi is that relative sign. So if you act, yeah. Good point, yes. Any other questions? Yeah.
Well, actually, when we talk about pi, when you check for pi was Hermitian, right?
Mm-hmm.
Did you assume, or does this imply that pi is a new function of x?
Pi is certainly not necessarily an even function of x. So let's just go through that in a little bit more detail. So if you take the Hermitian conjugate of pi, well, what happens? Well, these two operators here get interchanged. This gets a minus sign. This coefficient here, you get a minus sign right there. Okay. And then you have to do a change of variables on your integration where p goes to minus p. Okay? And so that will put it back in this form of an e to the plus ipx instead of e to the minus ipx. And then you might worry that you would get the d3p will change as well. You'll get a minus sign. But then you have to reverse the range of integration to keep integrating from infinity to minus infinity to infinity.
But so when you do A dagger
Mm-hmm.
and AB full dagger, you get A minus 4.
Yes, so just to say that, so AP minus A minus P dagger is A minus P minus A P dagger, okay?
So when you
And then we made the change of variables where P went to minus P, and so this became A P minus A minus P dagger. I guess I could call that P prime or something, that change of variables. It's a good exercise. Great. So now you have something else to do if you can't fall asleep tonight, which is verify that with these expressions, pi and phi are Hermitian. You actually have to be a little careful to get all the signs right, because we had, when you do the dagger, these two terms get interchanged, but with p going to minus p, there's this term here got a minus sign, so then you had to do a change of variables to take p back, where you take p to minus p, which takes those two terms back together and then gives you a plus sign, and then you have to be careful with all of the signs with the integration measure and so on and so forth. It's not like, it's the sort of thing, if you don't think about it, it's obvious. If you think about it a lot, it's obvious. If you think about it a medium amount, it's kind of confusing. So I encourage you to go through and work that out if it's not clear. Good questions. Yes. On the problem set this week, you'll be doing all of this for a complex scalar field. So that's going to be a great chance for you to hone your skills as quantum field theorists. Any other questions? Okay. So what I want to do now is just kind of end our discussion of free scalar field theory with a return to the notion of causality in quantum field theory. So the first thing that I want to do is I want to remind you is that so far we've worked in Schrödinger picture, where an operator, phi, is labeled by a point in space, and the states are time dependent. So in particular, if I wrote down one of those one particle states that I wrote down before, and that's a one particle state, say at time t equals 0, to evolve to some later time, you'd have to multiply by e to the IHT. Okay. Instead, what I would like to do is use Heisenberg picture So in particular, the operators that I will consider are now functions both of space and time, and they're related by the operators that we considered before that just depend on space by some multiplication by some factors of e to the IHT. So here, by phi just depending on the spatial variable x, I mean the Schrödinger picture operator. And here, when I write phi depending on x and t, or just on the symbol x, on the 4-vector x, which I've written here without its index, I mean the Heisenberg picture operator. So what I want to do now is write down explicitly what these Heisenberg operators look like in terms of those raising and lowering operators. So in order to do that, remember that phi was expanded in terms of the raising and lowering operators A and A dagger. So what happens when you take one of these A's or A daggers and conjugates them by e to the IHT? So remember that H here is the integral d3p of omega p times the number operator that measures the number of excitations of momentum p. So if you took AP and you conjugated it by e to the IHT, what would you get? Well, here, let me call the index of integration, the thing I'm integrating over for H, I'll call that P prime. When P prime is not equal to P in this expression, those e to the IHTs just move through and cancel one another. So you only need to worry about the case where P prime is equal to P. And then what do you get? Any volunteers?
Phase factor.
You just get a phase factor. So you get AP times e to the minus I, here, let me call it EP, I guess. That's what I did last. I changed my notation. E to the I, EP, T. Right? I mean, another way of saying that is that what you do is you take whatever state you want to act on this operator with, you think about it expanded in terms of all of the eigenstates, you get a phase factor e to the I HT, and then you have to do your lowering operator. And similarly, e to the IHT AP dagger, e to the minus IHT, well, you can just take the complex conjugate, or the adjoint, of this expression. And then this allows you to write down the formula for the Heisenberg picture operator in terms of the raising and the lowering operators. So we have that normalization factor, the e to the IP. And then what did we have before? Well, before we had an AP e to the I p vector dot x. Okay. But then when you just need to add in this factor here, and what do you get? That turns that e to the I p vector dot x vector in e to the I p dot x. Okay. Where p dot x just means p mu contracted with x mu. So what is that? That's p0 x0 minus p vector dot x vector, where here p mu is the 4 vector whose components are EP and P, so that P0 is equal to EP. And again, I remind you that our signature conventions are that when you lower an index, you get a minus sign. Okay. So I guess I need a minus sign here. And then similarly, we have a minus IP dot x. And then here we have an AP dagger times e to the I p dot x. Good. So going from Heisenberg picture to Schrodinger picture to Heisenberg picture is something that it's about the easiest thing that you could do. All you need to do is replace your vector indices by 4 vector indices. Okay. So this formulation treats space and time much more democratically. In particular, these phase factors here now reflect the full 4 vectors rather than just the 3 vectors. Any questions on that? So we're now ready to go back and revisit the question that we began this course with, namely that of causality. So in particular, the first thing that I'd like to compute is the amplitude for a particle to move from some point y to another point x. So this is the correlation function between phi of x and phi of y. We hear x and y denote points in space-time. So x here is shorthand for x mu, and y is some shorthand for some 4-vector y mu. And the computation of this two-point function is now reasonably straightforward. It's the kind of computation that we've already done twice so far, once last class and once this class. So we just plug in our expression for phi in terms of the raising and lowering operators. Okay, so you have an e to the I p dot x minus I p prime dot y prime, dot y. You have a normalization factor, 2 times the square root of EP minus EP prime times EP prime. And then you have the two-point function. So here, again, as I did before, I'm going to do the change of variables where I take p to minus p in that second expression to write phi as the integral of e to the IPX of AP plus a minus p dagger. And so we'll get AP plus a minus p dagger times, well, the same expression with p primes. And we just compute the expectation value of that in the vacuum state. Now, what is that quantity that we're computing the expectation value of? Well, remember that AP annihilates the vacuum when you act on it from the right, and AP dagger will annihilate the vacuum when you act on it from the left. That's just the Hermitian conjugate of that equation. So you just get the vacuum expectation value of AP dagger times AP times a p prime dagger acting on the vacuum. So if those two objects will commute with one another, then you can move them through one another with no cost, and you'll get 0. So the only thing that you're left with is the commutator, 2 pi cubed times the delta function, p minus p prime. So you can then use that delta function to do the p prime integral. And the expression you get for this correlation function between phi of x and phi of y is the integral d3p over 2 pi cubed times this normalization factor times e to the minus I p times x minus y. Sorry, I think I forgot a minus sign there. Good. So this is a very important object in our theory. This is the basic observable in our theory. Okay. So remember, phi is the observable, which is an operator. But the things that you actually measure are the expectation values of operators in various states. And this two-point function, d of x minus y, is the sort of most basic observable that you could imagine measuring in this theory. So let me make one comment, okay, which is that even before I did any computations, I wrote this thing as a function of x minus y rather than as a function of x and y. Now, when I did the computation, it turned out that it was a function of x minus y. The reason why it was a function of x minus y is translation invariance. In particular, the theory that we're considering is translation invariant. What I mean by that, well, more precisely, and maybe I'll find out a problem where you can work this out explicitly, but what we mean by that is that the vacuum state P has zero momentum. It's annihilated by the total momentum operator that we wrote down. And you can use this to prove quite easily that any two-point correlation function that you write down has to be a function only of x minus y. To say that a little bit more straightforwardly, if you have a theory with translational symmetry and you compute the correlation function between an operator at one position and an operator at another position, it can only depend on the distance between those 2 points. So in all of the theories, I believe in all of them, maybe not quite. In most of the examples we'll consider in this class, of course, we'll have translational invariance, although there may be some interesting problems where this property is not true. And then this 2-point function that I've written down would be something more complicated. Okay? For example, if you were considering electromagnetism in the presence of some conducting surface, okay, then that would break the translation invariance, and you might get more interesting expressions for correlation functions. Okay, let's see. Yes? Is there a p prime somewhere that I missed? Oh, no prime there. Thank you. Prime there. No, wait. No, I think I got it right.
No, I mean in the expectation value 0.
Yeah, I think I got that right. I think I got it right. Yeah.
All the daggers are half minus p
Oh, minus. There's a minus. Sorry. Yes. Minus. Thank you. Sorry about that. Then there's a plus. Ah, and then there was no minus here. Good. Okay, I did not make a sign mistake. I made a different sign mistake. That's always nice. Okay, thank you. Then maybe there's a plus here? Okay, sorry. Maybe there was a, let's see. Yeah. Sorry, I might have gotten one or two of the signs wrong here. I think that there was a minus sign here. Yes, good. There is a minus sign there. And then this sets p prime equals to minus p, which turns that minus sign here into a plus sign. Okay, because there were two minus signs. Good. Excellent. Any other questions? Thank you for that. Good. Okay, I see that I'm out of time. So next time what I want to do is just investigate this a little bit more thoroughly before moving on to some other topics. So probably next time will just be spent doing Green's functions and stuff like that. Maybe remind me, how many of you have seen the path integral formulation of quantum mechanics? Most, but not all. How many would appreciate a review of it, even if you have seen it? Some, but okay. Even some of the ones who have seen it before. Okay, good. I'll see you guys all on Thursday. Thank you.